So you guys can see my screen?
Yeah.
Yes.
Awesome.
Good.
It's my pleasure to present my friend Susan Mulagi. She was at the SETI Institute, then at NASA, and now at Space Telescope Science Institute. So she's a specialist in transiting planets and variable stars, heartbeat stars, and white dwarfs. And she's a winner of the NASA Excellence in Research Prize. So Susan, the floor is yours.
Thank you, Kepler. Thank you all for inviting me to be here. And thank you for allowing me to give you a somewhat vague title for my talk, looking for planets in all the wrong places. I'm going to kind of focus on some of my exoplanet research that I've done over the last 5 or 6 years. If at any point anything goes wrong, feel free to interrupt me, or if you really have desperate questions because I've gone too far or whatever, again, feel free to interrupt me. I'm a scientist at the Space Telescope Science Institute, but I'm also, that means I split some of my time between doing functional work to help NASA's missions run. And right now, that has included things like working on JWST, but right now it means I'm acting as the head of the MAST archive, which holds the data for JWST and HST and Kepler and TESS, which I hope are missions that some of you at least are familiar with. And so feel free to ask me questions about what that means as well, if you would like. And I will end with a small advertisement that I think you will all find interesting. So for this talk, I'm going to focus on exoplanets. And it actually feels very appropriate. I was just looking through my Twitter feed and was reminded that today is the conjunction of Jupiter and Venus. So we have, if you look up in the night sky tonight, you should be able to see Jupiter and Venus right on top of each other, which is super exciting. And the topic of this talk is essentially about looking for both Earth's and Jupiter analogs. So just to set some context, let's talk about exoplanets. At this point, we've been steadily finding more and more exoplanets. And this is just a discovery, number of known exoplanets per year that was put out by the NASA Exoplanet Archive last year. And you can see that, there's a variety of methods by which we find exoplanets, many of which I'm sure you in the room are familiar with, looking for that wobble, started by looking for that wobble from the radial velocity methods. But then when time series data from space missions like Kepler with those long baselines, we were able to add loads and loads of transiting exoplanets. And so right now we're looking at, have just entered more than 5,000 confirmed exoplanets. And see, I'm still trying to figure out which keyboard I'm using. So my timing's off, there we go. And you can see that primarily these exoplanets split between about 30% of them are gas giants, another 30% are something like Neptunes, another 30% are super Earths, with a small fraction that are actually terrestrial small planets like Venus and Earth and our own. And it's just because those smallest planets are so hard. And the gas giants is actually where there are far fewer, but at least where we've been able to look. Are you still getting me? I just got a notice that my internet was getting funny. I think we're okay. Yep, looks okay. Okay. And so these are the exoplanets we've found so far. But if you take a closer look and you actually look at how these are distributed in mass and period, or in radius and period, like you see on the right. And this is just split up by different types of methods for finding them. And for radial velocity, the natural unit is to measure things in mass. You're sort of getting a mass of the exoplanet by how much it tugs on the host star. But for transits, you're blocking the light of the star, and so you're dimming the star by a certain amount. And so radius is far easier to measure, and you're then using physical models in order to convert between the two. So that's why this plot is in both mass and in radius. But it shows you that there's basically this detection line out there as you get to longer and longer orbital periods. And in fact, if you throw on this plot exactly where Jupiter, Neptune, and Earth lie in our own solar system, you can see we haven't actually been able to detect planets like those in our own solar system yet. And it's not that they aren't necessarily there, it's just that our detection methods haven't gotten to the point where we have long enough baselines and or good enough signal to noise in order to get down to or out to where these planets are. And so there's a lot of parameter space out there yet to explore. And some of this, if in terms of at least understanding the statistics of exoplanets, is going to be spectacularly solved with the Roman Space Telescope that will be launching in, I think, 3 years now, they're saying. So maybe in 3 to 5 years, we'll have statistics from microlensing. And these are singular events that happen from microlensing. And so you'll find a planet, but you'll know no more than the mass of those planets and about its separation from the star. But still, it's very exciting because it would give us a sense of what planets, how common planetary systems are across our galaxy. So this is coming up. So keep that in mind as I go through the things I'm going to talk about today. So I've sort of split this into two, where I'm going to talk about some of my older research working with Kepler and where it has progressed over the last few years in terms of how we're going about counting Earths. And then I'm going to switch direction entirely and go back to my beloved white dwarf stars and talk about actually searching for planets around those white dwarf stars. And my title is probably extremely appropriate because it's really all about the to finally find them. And so there's a lot of work to be done by the end of this, but we will talk about planets along the way. So all the friends we made along the way. So let's start with searching for Earths from the Kepler mission. So just to remind you, Kepler launched in 2009 and operated to 2013, and then lost its second reaction wheel and switched into the K2 mission. It was intended to stare at the night sky and measure the brightness of stars, about hundreds of thousands of stars every half hour for 4 years. And it did that for 4 years. I'm only going to talk about the Kepler mission and its search to measure the frequency of Earth-like planets in the habitable zone of sun-like stars. So in this case, I'm looking for terrestrial planets, things that are just about 1 Earth radii, and planets that are about one AU away from stars that are G-type stars, thinking that those will be in a temperate zone where water could pool on the surface. And that's what we mean by the habitable zone. It does this using the transit method. The data that came down from Kepler was exquisite and it was long. I don't actually imagine in my life I will be able to have such exquisite data sets again. I came working on the Whole Earth Telescope. We were looking at variable stars of white dwarfs. And we were lucky when we could get 3 or 4 weeks of about 80% coverage over those 3 or 4 weeks. And then suddenly I moved to working on Kepler, and we were getting constant observations for full years on a star. And all this data and how to deal with it was just I don't know, paradigm shifting for me and how I thought about data. But Kepler's data not only was long in baseline, but it actually could, because it was in space, and even though it's only a 1 meter telescope, get really high precision photometry. So from Earth passing in front of a sun-like star, it could measure that very small dip, that 80 parts per million that you get from an Earth passing in front of the star. And it would do it as it did it over and over again. So you're hoping in 4 years, you would see 3 or 4 transits from an Earth passing in front of a star in a 1 year orbit. The transits that you see down the side are actual Kepler data from Kepler 37. And what's nice about this is one of the smallest planets that Kepler found. And so that first one, Kepler 37b, you can see is a 20 part per million dip. And this is the precision Kepler needed in order to find Earths. And if you can't find Earths, you can't measure the frequency of Earths. And so for some stars, we definitely had stars that were quiet enough, the signal to noise was good enough that you should be able to see Earths if they're there. And so Kepler did this. There was a pipeline that went through and searched for Earth out of that big, long data set. You can imagine an observation every half an hour for 4 years straight. And it found transits like you see at the top here that happen periodically by doing like a matched filter where you said, this is what the transit shape I'm expecting. Anytime you see something like this, return it. In addition to doing that, it also found things like eclipsing binaries, the second one down, but also things like star spots and things like variable stars and things like noise in the data. And so we ended up after the final run, we had our cleanest light curves ever, we had this final run where we said, give us everything that looks like planets. And we ended up with almost 40,000 different things that we called threshold crossing events, TCES, that we needed to weed through to say, wait, which one of these are planets and which one of these are other stuff we don't care about? And so to do that, initially we were doing this by eye, but that became a lot of work. And this was before machine learning really became a popular item that you could just pull out of the box. And so we invented something we called the RoboVetter, which we named Dippy. And it's essentially you measure properties about each of the transits to like the shape of the transit, whether each transit looks the same from one to the next, whether it's near the edges of a place where there was a gap in the data. Items like these, we gave to Dippy, the RoboVetter, and said, tell us if you think it's a planet or not. And he did. He said, that's a planet and these are not. And that's essentially the methods. And so we did for about 2 or 3 years, we worked to refine what those metrics should look like. But those metrics were very specific to the Kepler data and the types of false positives we were seeing. And as a result, we went from about 34,000 TCEs down to 4,000 planet candidates. The other reason why it was so very important to have this automated is we didn't have to just look at the actual data. We needed to look at simulated data that had injected transits and simulated false positives in order to measure the frequency of planets around these stars, because we wanted to measure how well our vetter was doing. And I didn't want to do that by eye. I wasn't going to look at another 100,000 of these events to find fake planets and try to do it consistently as a human. So that's why we invented this RoboVetter. The real tricky part, actually, for that particular question of trying to find Earth-like planets around sun-like stars was actually what we started calling false alarms. And there was 2 primary sources of these false alarms. One is stellar physics, and the other was instrumental noise. People started getting angry at us when we called it stellar noise because it's actually stellar physics. But variable stars, by the time they came through and got detrended, like the example I'm showing here, might look exactly like a transit. And so you'd have to go back to the original data to identify that it was stellar physics. There's also cases where you have such short period or even long period variability that of a low level that it was hard to sometimes tell that it was stellar physics or that was causing these things that look like transits. The other issue was, and was in many ways is far worse, was the instrumental noise. We had this issue with the Kepler detectors where there was a bias level change that would go through it when it reached a certain temperature, essentially. And this is something they called rolling bands. That bias level would kind of roll through the detector. And only certain detectors had this problem. And so the way Kepler observed is it actually looked at the sky for 90 days and then it rolled 90 degrees. And so stars would move between different detectors on Kepler. And so as a result, a star would roll into one of these detectors that had this high noise property from what we call rolling band. And so what you see here is noise once a year. So you look at those blue triangles, and then once a year, you suddenly see lots of noise. And so our detector would go in and see noise like this and go, that's a planet. Look, it's even a planet at 1 year period. And in fact, if you plot up all of those threshold crossing events over as a histogram by period, you notice there's this huge buildup around 300 to 500 days, right where I wanted to find my Earths around around sun-like stars. That is absolutely the wrong place to look for planets, because there's it's the biggest haystack you could imagine looking in, and there are very few needles in there, because only very few stars were quiet enough that we expect to be able to actually find these transits due to small terrestrial planets in a 1-year orbital period. But the RoboVetter actually did an admirable job. You notice that what I have on there, what we call our Kepler objects of interest in yellow, which weeded out much of that haystack, much of that noise, and also the things that we finally called planet candidates is in blue. So that RoboVetter took 40,000 or so TCEs and whittled it down to about 4,000 planet candidates, things that actually looked like transits. And this was the final catalog that came out in 2018 by doing this. In addition to that, because we did this by a RoboVetter, we had actual measurements of the shapes of the transits, of all sort of the odd even effect, all sorts of things about those transits. And each of those measurements actually have an error on it. And we propagated that error through to the decision we made, whether it was a planet candidate or a false alarm, and then ran sort of basically a Monte Carlo simulation where we said, well, let's, pretend, it varied between those error bars and see how often it actually failed the RoboVetter. And that produced this score. So if it failed half the time we ran that Monte Carlo, you got this disposition score, a reliability score of 0.5. And so things with a 1 means, oh yeah, it'll always pass. Looking at that, that's a clean, beautiful transit. Then we have a bunch of things that were maybe iffier. The error bars were so large on some of those metrics that it could just as easily be something that is essentially noise or stellar physics or something else. In addition to this catalog that you got out, but you can see out at long periods, it tails off kind of as you would expect. And there as a function of period. Along with this catalog, we produced measurements of how well we did at making the catalog, which is key for anybody who's actually going to do statistics with it. Because you not only needed to know, here's the things I found, but how many things was I actually able to find planets in? And so how good is this catalog? So we measured completeness by injecting transits into the light curves, and then tried to recover them with the same system, all same pipeline to find them, and the same RoboVetter to vet them. And this is just a basic 2D histogram in terms of signal to noise and period, showing that we did very well at big planets, high signal to noise planets at short periods. But when you get out to 200 to 500 days, you start to miss some of the planets because they end up being hidden by other features in the data, essentially. And so our completeness would drop off. We'd only find about 73% of the planets that were actually there. So one of our jobs at RoboVetter was to make sure that completeness number got as high as possible. We also then measured the effectiveness. How effective was our RoboVetter at removing the haystack, removing the false alarms? And we did this really well at that. We measured this in 2 ways, with simulating false alarms in 2 ways. This is a very tricky thing because you don't really always understand all your noise sources. And so we needed to find a way to make sure not only that we had those noise sources, but they were in there at about the same occurrence, at the same frequency that is in the real data. And so what we did is we flipped the light curves over and assumed the noise was symmetric. We also scrambled the data by quarter. So we bring quarter 4 to the front and 1 next, and then 3 and then 2 like this. And through that scrambling, we would simulate false alarms that way. We're hoping to kind of take out any of the periodic signals because they wouldn't be in the same place throughout the data. Though in the end, we still kind of had to remove some of the planets in order to get decent statistics, because they would find them just at the wrong periods and it would get confusing. But through those simulations, we were able to simulate our false alarms, and our RoboVetter found 99% of all the false alarms there, which all looks great. And then you get to that last figure on the far right, which is the reliability of the catalog. It's not just enough to remove them all. You need how many planets are left, how many false alarms are left, and how many planets are left to give you the reliability of that final catalog. And if you look out there at that long period, low signal to noise box, we're only the final catalog is only 30%, 37% good. 37% of those things are actually planets, and the rest are probably false alarms. So that's worth knowing anytime you're using the Kepler Planet Candidate Catalog. It's not meant for some people to go out and say, there's a planet. It was meant for people to do statistics and try to measure occurrence rates, specifically of this value of A to Earth, and how common are planets in one-year orbits, terrestrial planets in one-year orbits. And with these pieces of information, we have not only found some planets, but we've also measured how the ones we missed and the ones that have gotten through all of our robovettors. And so we have, between the completeness and the reliability, people are able to do occurrence rates. And that's what they've been doing since 2018 when all of this came out. So a lot of Kepler's big results, which are worth mentioning, came before even we got to our final catalogs. Essentially, the exoplanets, Kepler just blew away our understanding of exoplanets, especially small ones. These are just kind of the big highlighted things that I always tell people, this is what Kepler did. It found out that small planets are more common than big planets. We actually have measurements now of super Earths and of sub-Neptunes, where before we really didn't. And we found things like that Neptune desert, because we know we should have been able to find planets there, and we didn't find any. Additionally, we have, as we improved our catalogs for the smaller planets, found that there's actually a gap in the occurrence rates right around 1.75 times the radius of the Earth. And this seems to be due to the star eroding away the planetary atmosphere, so changing sub-Neptunes into super Earths. And so creating kind of a natural gap between these two types of planetary systems. And this was a result that came out right around the same time that the final catalog for Kepler came out, though it was a result that was actually predicted by theorists, Owen and Wu, in 2013. Said, yeah, there it is. It's always exciting when it's right. And then finally, it's one of the big takeaways from Kepler, because of occurrence rates, especially around M-dwarf stars, that we're finding loads of planets around just the small sample of M-dwarf stars that Kepler observed, that because they have so many multi-planet systems, there must be more planets out there than there were stars. And I know this is one of these things that these days, we've been living with this for 10 years now, so it feels common, and of course, but back when I was in graduate school, we did not know this. We didn't know there were planets out there we could land on, even if we did fly out to another planetary system, because all we knew about were hot Jupiters going around stars. And so this is what has happened due to big ideas and the Kepler Space Telescope. But I promised you a little bit more about the frequency of Earth-like planets around sun-like stars. So at the end, we actually did get a handful of Earths, and these are them. And this is shown as a stellar effective temperature on the y-axis and insolation flux, so how much energy it's receiving from its star in terms of solar flux along the x. The real problem was when we released this catalog, it was right before Gaia Data Release 2 came out, and suddenly, once that did, all of our stars changed. And if you one thing about the transit method you should remember is that it's a relative thing. So if we don't know the radius of the star, we don't know the radius of the planet. And so if my star suddenly increases by 20%, then my planet's also going to increase. And so that happened about a year later, that Gaia stellar results came out, and we were able to completely redo the Kepler catalog, and that changed all of the planet parameters, and it removed some of these planets. It made some of my planets bigger. And so this is work done by Travis Berger in 2018. And so these are now the habitable zone candidate planets that are smaller than 2 Earth radii. And one thing you can look at is there are very few that are actually the size of Earth, which is the size of the circle I'm showing on that plot. But there are quite a few. I'm also showing that disposition score, that reliability metric I gave you as the color bar. So those things that are dark in color are likely really good solid planets, whereas all those ones that are yellow, well, maybe. But even then, there are very few that are actually the size of Earths. And if you go and look at individual ones by eye, even some of the ones that really do look like Earths, you're kind of like, I'm not sure I would believe that. But even with this catalog, people have gone to town trying to determine the frequency of Earth-sized planets near in the habitable zone of some like stars. And here is kind of a summary of the results of where we're at with this. These are all the occurrence rates. If you just look at the blue ones, the red ones are for M-dwarf stars, but the blue ones are around essentially FGK dwarfs. And essentially using the same Kepler data set, this is the range of error values and their error bars that people are getting for the value of what we call eta Earth. And you can see two very recent results I've outlined in purple. One by Steve Bryson just a couple of years ago, using the entire catalog, using all the completeness and the reliability metrics. And he gets a range of about somewhere between 25 and 175 planets per 100 stars, which is a lot of Earth-like planets. Planets might be everywhere. But then another study that came out just last year tried to correct for that that sculpting effect that's happening at short periods. Because the problem is that people, since we only really have solid knowledge of planets around down to like 2 Earth radii, for very short orbital periods. So you're extrapolating out to really get that value for eta Earth. And a lot of these are doing an extrapolation to get out there. But at shorter orbital periods, you're affected by that sculpting effect from the photoelectric, from the Fulton gap that I was showing you before at 1.75 Earth radii. And so as a result, there might be more Earth-sized planets might be more common at shorter orbital periods than at longer orbital periods. And so that Bergston paper attempted to correct for that and then got a much lower value, something around 25, or I think even 15 was his nominal value for 15 Earth-like planets in the habitable zone per 100 stars, GK type stars. So there's kind of a lot of error bars, and people are attempting to try to figure out ways to make our understanding of this value of eta Earth more secure. And there's kind of low-hanging fruit for people who are willing to put the effort in. Like, the problem is that in part, each of these are using a slightly different stellar sample. They use a slightly different methodology. They incorporated that reliability of the planet candidates in different ways. They each extrapolate in different ways. Some of them even have different definitions for what the habitable zone are. So that's another reason we see these variations. And so people are talking about putting in data challenges to try to at least try to understand where it is that reasons we're getting such different values. One project I did work on to try to improve the reliability of the catalog, or one idea we had, was that you could try to reobserve the transits for the candidates that are the most Earth-like using the Hubble Space Telescope. And we did it for one, Kepler-62f, which is a confirmed planet, but it kind of ended up in the iffy category for our in the final catalog. And so this is actually Hubble data that was taken by Chris Burke to recover that transit. So we said, this is when it should transit next. And we said, use Hubble to go find it again. Because if we see it again, that means it wasn't just noise. It wasn't just noise from the Kepler detectors that caused this thing. And in fact, when we took it, it was actually on top of also the transit of Kepler-62b. So you actually ended up with 2 transits at the same time, which is why that model looks so funny. But the Hubble data is a challenge to work with. And the other problem is that each of these transits, you would need about 15 hours of Hubble time just to recover the transit, which is a difficult thing to get through a time allocation committee. But it is a potential way to go back and essentially validate that these planets are real, and would improve the reliability of the catalog. And that would check off one of the dominating error bars for our understanding of eta Earth. So as I leave this topic, and I just wanted to mention why eta Earth has come up so much. And you know, some people, eta Earth is interesting inherently just because we have sort of a desire to understand how common, you know, life is in the universe and how we relate to it. Like, is Earth the only place there is? And that has fed into a lot of the goals for NASA's next big mission when they're looking 20 years out. And this is a mock-up that came up. And so even And so even that next flagship mission that NASA's planning, they called the Habitable Worlds Observatory. So in order for that mission to be a success, they need to be able to image and take spectra of a habitable world, which means a terrestrial planet likely in the habitable zone of a sun-like star. And so this value of A to Earth is important because it directly feeds into our feasibility of being able to do this mission. Like, what specs does that telescope need in order to be able to examine the atmospheres of a handful of Earths? Because the fewer there are, the farther out we have to look in order to be able to image an Earth-like planet. And so that's why this value is important. That value, they basically set a value in the decadal review when they were deciding what to do next. And if that value is very wrong, we could end up with no ability to actually measure Earths. But we will know that they're not there then at the end of the day, once they finish this mission. I'd like to know before we get there. And as I mentioned before, it looks like Roman might be able to reach Earths, and so may be able to answer that in the next 5 years. It would be nice to have both a Kepler and a Roman number to compare together to have some security in our understanding of that. Okay. I'm going to move on to the second act of my talk now, but I feel I should pause in case I'm completely confused or if there's a desperate question. I'll happily take them at the end otherwise. Okay. Awkward pause. All right, I'll keep going. So we've talked about Earths. So what are we doing how can we go about looking for Jovian analogs instead, Jupiters and Saturns? Because as I mentioned, they're too far out for radio velocity surveys have been taking data now for a very long time. And so now they're pushing out to find longer and longer orbital period objects, which are now pushing into things that are at Jupiter orbit. So they are finding Jupiters at this point. Things that are Saturn size and below are going to be a little harder. So this is kind of the stage we are at. So here, this is actually far more recent than some of the other plots I've shown you. This was made just last month. And so this shows the kind of the cloud of radio velocity planets. You can see how they're getting down into Jupiters, but it's probably a while before they'll push into Saturns. At the same time, direct imaging, where they actually block the light of the star and then can find a planet that's sitting around the star, have actually now found dozens and dozens of planets. They all tend to be very young because you have to have the remaining heat from the planet in order to see these things. And they need to be bright enough compared to the glare of that star, even after you used a chronograph to block out the light of the star. And so they mostly find things that are like, tens, a few times the size of Jupiter, but they're now also pushing down to Jupiter masses. This is a good point to remind you that I've now changed all the axes and we're looking at masses instead of radii now, and that we're comparing it to Jupiters now instead of Earths. So things that were one before are now Jupiter masses instead of Earth sizes, which most talks don't do that in the middle. So I wanted to take a moment and make sure we are all up to date on that. But I put Jupiter and Saturn on here, and Uranus and Neptune are at the bottom, though they're not labeled. Just so you can have some bearings is what we're looking at. So this is where we are. We can find things that are Jupiter using radio velocities. We're starting to come down towards Jupiter-sized planets with direct imaging, but they're very young planets around main sequence stars. But I'm going to argue that we are at a good time to start another search for planets around white dwarf stars. And white dwarf stars are actually a great place to look for planets. Not only because white dwarf stars are awesome, but because they're actually can make it easier to find these planets and give us a chance to look at a different sample of planets than what has been done so far. So first of all, white dwarfs are inherently dim, right? They're the size of Earth. And so they're 10,000 times dimmer than their main sequence star. And that means that if you look out like in the mid-infrared, and I happen to know a mid-infrared telescope that recently launched, if you look out in the mid-infrared, the ratio between the brightness of like a Jupiter planet and a star is only about 100 to 1, which means they're similar in brightness. They're not, one is hiding in the light of the other. As a result, no coronagraph is necessary in order to see the light from that Jupiter-sized planet. The other thing to remember is that after the star goes through post-main sequence evolution and loses all that mass, planets actually move outward. Because all the mass is lost from the star, the angular momentum conservation says any remaining planets should just move out. So that basically the orbit's all widened by about a factor of 2 here. I'll zoom in on this because I thought that might be a little too small. So Jupiter moves from 5 to 10 AU approximately, Saturn from about 10 to 20 AU. And so because they're farther apart, if you're trying to directly image the planet, they're going to be more separate from its star and therefore easier to see. And finally, white dwarf stars, even though they're the end stage of, for a lot of stars, are not actually that old, but they're kind of middle-aged, right? And Jupiter is kind of middle-aged. So this gives us an opportunity to find planets that are middle-aged, kind of like our own Jupiter. And so if you're looking at a planetary system, a white dwarf that had an A to F star progenitor, you're looking at things that are maybe 1, 2, 3, 4, 5 giga-years old. So maybe more like the Jupiters in our own solar system than all those very young baby planets that we've been finding by direct imaging. I threw this in here because it's the only graphic I could find, just to remind ourselves what we expect to happen after the evolution of a solar system after the star evolves off the main sequence and becomes a white dwarf. And essentially, you expect that he goes through that red giant stage, and then the inner planets are all engulfed or disrupted to the point that they're destroyed by the star. But we expect basically Mars and outward to still exist. But as I said, the mass is lost from the star, which causes those planets to move outward. In fact, it was interesting, I was reading some of the literature, and it's possible that Jupiter and Saturn will end up in a new habitable zone around our red giant sun at some point, and so might get heated for a little bit even. But then it turns into a white dwarf after it loses all that mass, planets have moved outward, then those giant planets in the planetary system can disrupt asteroids and comets in that planetary system, causing them to go into eccentric orbits and potentially go within the Roche limit of the white dwarf, be tidally torn apart, turning into a debris disk, and then rain down onto the white dwarf star. And we've seen this evidence of this through polluted white dwarfs for decades. Right now, I believe it's about 50% of white dwarfs have some evidence of metal lines on the surface. This was not expected when we first found it. White dwarfs are extremely dense. That means the metals are raining out of should be raining out of the atmosphere on timescales that are potentially as short as a few weeks, which means that they're constantly being fed by something. Something is falling onto the white dwarf, causing these metal lines like calcium and magnesium and silicon. And so it's believed that that's rocky material coming from a debris disk around the white dwarf. And one of the popular theories as to where that debris disk is coming from is that the surviving giant planets perturb those orbits, as I mentioned, which cause them to fall towards the white dwarf, get pulverized into this debris disk. And we see plenty of evidence of debris disks around white dwarfs, including ones that can contain hot gas and dust. And they tend to be connected to things with metal lines. So this means then that anytime we see metal lines in a white dwarf, that implies that there's a giant planet out there for us to find. So this is exciting to me because it even tells me where to go look for giant planets around white dwarfs. And in fact, this is not a new idea. I'm not complaining this is all a new idea at all. People used HST and Spitzer to look for planets around white dwarfs. And I'm not going to do a full literature search for you this has been going on, as I said, for decades. But for instance, using direct imaging, John Davis, for instance, looked at about 4 or 5 metal polluted DAZS white dwarf stars with HST. And was able to put limits of about 10 Jupiter masses. So he was sensitive to very large planets. And this is an image from his paper from HST. And he identified candidates, but none of them were really the right color to be considered a planet. Also, the other technique people use is infrared excess. If the planet, and you can't resolve the planet from the white dwarf, out at those long wavelengths, mid-infrared with Spitzer, you should be able to see the light from the white dwarf change that Raleigh Jeans tail that you expect from the light from the planet will change that Raleigh Jeans tail from the white dwarf. And since it went in the red line here this is again from a paper by John JWST in 2007, since the red line is that tail, the photometry points you see don't do that. So he was able to put limits of about 20 Jupiter masses, but if there was a white dwarf, you would see that slope change and you'd see an excess of flux there. And this was done for hundreds of stars using hundreds of white dwarfs using Spitzer. With these sorts of limits. But that said, people have started finding planets around dwarfs, so they do exist. Here's just a highlight of 2. I believe the count is about 4 now, depending how you count. But these 2 are interesting and worth pointing out. So using transit methods, Andrew Vandenberg found a transiting planet called WD 1856 around a white dwarf. As you imagine, this is like an 8 Jupiter mass planet, and it has an orbital period of about 1 day. So it's super close to the white dwarf. It shows a huge transit because the planet is huge compared to the the Earth-sized white dwarf compared to this huge 8 Jupiter mass planet. And it's grazing. So it doesn't quite reach that flat bottom, or it removes all the light. This is a very interesting planet. But the question is, how did it get there? Did it form from the material? Did it form from remnant material? Did it migrate inward? It's an open question. There has been one microlensing planet around white dwarf found by Blackman in 2021. And I'm not going to explain microlensing to you, but the fact that you see little bumps on there and not just one singular rise and fall tells you that there's a planet at about 2 AU. That's approximately a couple Jupiter masses at about 2 AU from its star. So this one is far more in the category of the kind of Jupiters I'm hoping to look for around white dwarfs, except for it's 2,000 parsecs away, which means, and we probably can learn no more about this particular planet than what we see here. So that brings in the Webb Space Telescope. The Webb Space Telescope could be a wonderful machine for finding planets around white dwarfs. And so let me give you a quick reminder of the Webb Space Telescope. I assume some of you have paid attention to its launch over the last year and the release of many of its beautiful images. It's a 6.5 meter telescope in space out at the second Lagrange point. We put it out there with these great big 5 tennis court size sun shields in order to keep it extremely cold, because if you're going to observe in the mid-infrared, the near and mid-infrared, you need to reduce your backgrounds as much as possible. And we do that by being really cold because I want to see the universe. I don't want to see the heat from the telescope. So on the cold side, we have the telescope, we have the instruments, secondary mirror. But then on the warm side, which always points towards the Earth and the sun, we have the antenna to talk to us, a solar array to get power, rockets to steer and control the telescope. There are 4 instruments on this telescope: NIRSPEC, NIRCam, NIRISS, and MIRI. All of them do a combination of imaging and spectroscopy. I'm going to talk about MIRI, which is the mid-infrared imager, and spectroscopic machine as well. But I'm just going to use the imaging part of it. Using the NIRCam and MIRI, JWST has done a spectacular job of taking beautiful images. I'm just going to put one in here because I couldn't resist, and because it has a white dwarf in it, so I thought it fit in very nicely. This is the planetary nebula of the Southern Ring Nebula, both with NIRCam and with MIRI. And what I love is in MIRI, you can see you have those 2 stars that are only a few arc seconds apart from each other, and how spectacularly JWST was able to resolve those 2, because this is the resolving power it has. And the white dwarf is the red one because it's the one that's because it's encased in dust, and the other is an A star that's in this binary system. I don't know much about the Southern Ring Nebula, so I had to read it all up on Wikipedia when this came out. But it's a spectacularly beautiful image that now hangs on my wall in my office. But JWST has continued to do wonderful things for exoplanets. It's using transient exoplanets to look deep into the atmosphere as exoplanets, but it's also directly imaging nearby planets. This planet, for instance, HIPS 65426b, is about 100 parsecs away. And it was a planet we knew about before JWST, but it was imaged and at many different wavelengths, using both NIRCam and MIRI, using the coronagraphs on both of those instruments to learn more about its atmospheres and the physics of its atmospheres. And here's another example where they took spectra of kind of a exoplanet let's see, yeah, I think it's an L dwarf, a brown dwarf type planet. So somewhere in that border between the two, called VHS 1256b. And so it's just showing the power of JWST to not only image them, but to also take spectroscopy of exoplanets we can directly image. And in this case, they found evidence of water and methane and potassium and sodium. So this is the program that I actually put in, and we've just started getting data on. It's for finding planets that drive the white dwarf accretion. So the idea was we would look at white dwarfs that were DAZs and try to find exoplanets in two ways. One, we would look for infrared excess. We picked planets that actually we'd already tried to do this with Hubble, so we were able to already rule out down to about 10 Jupiter masses and knew there wasn't a debris disk, a big bright debris disk around it already. And with JWST, if we took 4-band photometry, so at 506, so these are the bands of the different colors. So that's at, at 5 microns, 7 microns, 15 and 21. And you then looks at what you would expect from the white dwarf, you can look for an infrared excess. And if you look at the one on the right, this shows you as a function of planetary mass, how much infrared excess you expect given a particular planet model of a particular age. And we should be able to see at a 2 sigma level, an infrared excess down to 2, possibly even 1 Jupiter masses when you look in the 2100 micron band. It's a little iffy down at 1, but certainly, so we use 15, you get a better signal to noise for like the larger planets. Just because the backgrounds gets higher and higher, but 21 is really necessary to get the smaller planets because it rises quickly there. This, of course, is all dependent on our understanding of Jupiter mass planets to begin with. We're also going to take a really deep image at that 1500 wavelength to try to directly image nearby exoplanets around these nearby white dwarfs. This isn't just a simulation of what we'd expect to find for 1 Jupiter mass planet at 1 arc second. So this would be like at 15 AU. So something that's just a little farther than where Jupiter would end up after the evolution of its star. And so because of that wonderful contrast we're getting, this is what we expect to see. This is the sample of the 4 white dwarfs we decided to target. You'll notice that we picked things that were as close as we could find, things we'd observed before, and things that were known to had polluted atmospheres. So all these are DAZs, and they all have relatively low ages. So they're all about a giga-year old. The younger it is, the easier it's going to be to find the white dwarfs. And so the younger it is, the less time I had to ask for on the telescope in order to find it. And given that I was observing for a telescope that hadn't even put this proposal in for a telescope that hadn't even launched, and I didn't really fully understand its performance, it seemed like it was best to go after things that weren't cutting, the edge of it. So each of these, that 1500 band is a couple-hour deep image, and then some pretty easy photometry points for the other 3 bands. This is essentially then the detection space that we expect to have for this survey of 4 white dwarfs. So this is just one of those white dwarfs, but you can see that for the unresolved survey, the infrared excess, that's going to give us planetary masses down to 1, maybe 2 Jupiter masses. But then we'll be able to, if you have things at wider separations, things that are like 10 to 12 AU and wider, we should be able to find those with direct imaging down to possibly less than 1 Jupiter mass. For some, we're down to about half a Jupiter mass. And thankfully, John Debus had already gotten down to 10 Jupiter masses for us on all 4 of these targets, or at least 3 of them, 3 of the 4 targets. So we're looking for the small things that are left there. The key here is when you work through the statistics, we can detect less than 1 Jupiter mass for all of the white dwarfs in this sample via infrared excess and direct imaging. And with 4 targets, since we expect there to be a planet in all of them because they're polluted, there's only a 19% chance we won't find a planet at all. And if that's true, if we don't find a planet, it's really going to throw that theory out of, people are going to really start to question the theory that it's giant planets that are driving that accretion. And the other thing, but if we do find a planet, these planets are going to be able to follow it up with photometry and spectroscopy, especially if there are a few Jupiter masses, maybe not the one Jupiter mass ones, but the ones that are few, we can hit them with many photometric points and we can learn things about their mass and their atmospheres. I wasn't able to get much of our data analysis done before this talk, but I wanted to show you some of the data. This is actually the 15 micron data from our first target, WD 2149. In the center, there's the white dwarf with that, what is now becoming kind of a common PSF that you think of for JWST. This is, so Misty Krekraft is somebody I work at the Space Telescope who was able to run the JWST pipeline well enough to actually get out this nice clean image. From our preliminary results, looking at these data by doing PSF subtraction, using fancier techniques, even like using kernel phase interferometry, if you've heard of that, we can get down to about half an arc second at sub-Jupiter, down to at least one Jupiter mass, and some potentially sub-Jupiter masses. So that means we're be able to see a Jupiter at 10 AU in these targets if one was there. So just to give you a sense of the size of the scale, I've kind of put a fake little Jupiter and a fake little Uranus orbit on there, just to give you a sense of where we would find those planets on the scale of this image itself. And so we should have been able to find those. It's not looking good for finding one this image, but the other thing I want you to notice though, when you look at this, is all the other stuff that's in the image. There's stars, certainly there's point source stars in there, but there's also loads of galaxies. I have discovered I don't like galaxies. They're everywhere. And some of them are point sources and some of them are very red. And so they're going to become our dominant sources of false positives. Remember how we talked about false positives with KEPLER'S? Well, it's all coming back for this project as well. Even if we find something there, we're going to have to rule out that it's not likely to be a false positive from either an M dwarf, like a background M star would potentially show up as one, but those are going to be easy to rule out from our photometry because they should just not be, they should follow a black body, whereas our Jupiter planet will get brighter as we go redder. Galaxies, however, don't have just they always look this way in 4-band photometry, but they do tend to look like ovals and smudges. So we can at least rule them out a little bit from morphology. The other thing is to worry about is asteroids, because they could be of random sizes and about that temperature. And so we have thought through how we can get it down to a reasonable statistics. So it's only like there's a 1 in 100 chance that it's going to be a galaxy. But at the end of the day, to actually confirm a planet, if we see one, is we're going to need a second epoch that shows common proper motion. Because if you remember, luckily, most of my targets all have very high proper motion. And so it only takes about 6 months to move about 1 pixel across a JWST pixel. So at the end of the day, if we find something, we're going to have to go and get a second epoch to be able to confirm that indeed it's bound to our star. If we did a larger survey, if they would give us the time to do a larger survey, and if you expect that planets are about as common around white dwarf stars as they are about their A to F star progenitors. A recent paper by Nielsen, 2019, says that planets are actually, these wide orbit Jupiter planets are actually more common around A to F stars than they are around their GK type stars. And so they came up with a value of about 0.4 to 2.7 giant planets per A to F star. This means that given this detection space shown by the blue that we could do with JWST, we should find, if we could, they'd give us the time to look at about 50 white dwarfs, we would find 20 to 140 giant planets that are potentially as small as Saturn. And now I admit this blue box is maybe not our best case, but it's a pretty good case, because you can imagine as you get farther away, the planets get dimmer. And so that actually brings up the bottom of it as the white dwarf gets farther away. Also, that inner line comes from your ability to directly image, and there was the separation between the star and the planet. So again, as you get farther away, it'll come in But this is not our best case. Our best case actually goes even deeper. So, so this would be like, I don't know, 400 hours on JWST if they give it to us. We could actually get a sample of white dwarfs, planets around white dwarfs, and start to really do statistics on what happens and what is the fate of Jupiter. So I will just conclude by saying, if we find 0 planets, it'll be exciting with these 4 stars, because we will be able to kind of rule out this theory that it's these giant planets that's driving accretion on the white dwarfs. And we can start to question, like, maybe Jupiters just aren't there. Maybe they're ejected from their system. But maybe we'll find a collection of planets, and maybe someday they'll let us do a bigger survey, in which case we'll start to have examples of evolved planets around stars and start to explore what the post-main sequence evolution of planets is. And we will also potentially find middle-aged Jovian planets whose atmospheres we can explore with JWST. So I will finish there, and it's 11:30. I'm sorry, I ran way over. I hope there's time for a few questions. And I'm just going to put this up as my advertising slide for something we're doing at MAST for anybody who's working with TESS or Kepler or time series data and are interested in working with data in the cloud. We put up a science platform where you can go and work with Jupyter notebooks and learn more about how to work with TESS data. And so feel free to go there. But I'll take questions now. I'm, again, sorry for going over.
Thank you, Susan. So we have questions, Emma?
And speak up because you're very quiet.
Okay, do you hear me?
I do.
Okay, very nice talk.